What's up, everybody? It's Dan from pshhh, and here with a video about Bayes' theorem, which is typically, well, it's definitely a probability concept. It happens to be featured in a student of mine's statistics class. Sometimes statistics goes over probability stuff. So here we are. This looks fun, doesn't it? So let's take a look. Suppose you have events A and B. The probability of A, given that the event B has occurred, is this. Now, this part right here, it's possible my student learned that even before Bayes' theorem was even mentioned, because that's just sort of conditional probability. Bayes' theorem says, though, that basically this whole denominator, if need be, you can do all this to find this denominator, okay? Now, I'm going to propose something to my student because he's got a midterm coming up. Whenever you're doing this conditional probability stuff and you think you might be using Bayes' theorem, just know that you're always going to be using, just always use this as the numerator, okay? So, Bayes' theorem says, oh, A given B, and then equals blah, 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 and it says probability of A and B. Well, I'm going to say go ahead and just use the numerator in, I'll call this, we've got the blue one, and we've got the green complicated one, right? I'm going to say always use the numerator from the green one. That's going to be helpful, okay, which you'll see. But when it comes to the denominator, it depends. When it comes to the denominator, if you can get away with just using this guy and plugging in some value right away, probability of B, then do that. All right. Now, I am going to tell you that when it comes to this problem, turns out that you can get away with just doing the probability of B. Okay. So we shall see how it works soon. Okay. So let's read the problem. Probability of a patient having liver disease is 0.1, and the probability of a patient being an alcoholic is 0.05. Also, among those patients diagnosed with liver disease, 7% are alcoholics. What is the patient's probability of having liver disease if they're an alcoholic? Okay, so that's the final question there. So we do want to be very sort of aware of the final question. And I'm going to say for a lot of probability problems, maybe even a lot of statistics problems in general, it's good to write down the cast of characters. Immediately start writing down variables representing certain pieces of information from the problem. So, for example, we could say that L, represents having liver disease. Have liver disease. Now, I want to distinguish from this setup, so I'm not going to use A. Let's see, what should I use for being an alcoholic? I'm going to use H, okay? Uh, alcoholic. Okay, so in other words, L represents the event of having a liver disease. H represents the event, we could say, of being an alcoholic. And the probability having liver disease, according to the problem, is 0.1. Okay, and we're talking about the population of patients. We're pulling from that population. So 0.1 of those patients have liver disease, and the probability of the patient being an alcoholic, so P of H, is 0.05. And there's another piece of information they give us. The other piece of information is they say also among those patients diagnosed with liver disease, 7% are alcoholics. So in other words, the probability of being an alcoholic, given that they have liver disease, is 7%. Now that's 0.07. Okay. So that's all relevant information. And then we get to the final question. What is the patient's probability of having liver disease if they are an alcoholic? So I'm going to actually do a little red underline here. because we're going to make this red. What they're asking is, what is the probability of L given H? Isn't that what they're asking, right? So that is huge to recognize the cast of characters and to recognize what they're asking. Okay. Now notice how I listed variables representing the event itself, and I represented the probability of those events and any other probabilities that they mentioned. Okay. So let's get cracking with this. Like I said, we always want to use the numerator of the green one. So we're going to say the probability of L, right, times the probability of the other thing, which is H, given L, right? That's going to be all over. Now, this is the probability of being an alcoholic, right? That's what that is down there, probability of being an alcoholic. Now, we actually have that. We have that number. It's right here, right? So we can actually get away with just using that very simple denominator. So filling in the values, the P of L, probability of L is 0.1. The probability of H given L, the probability of being an alcoholic given the fact that one has liver disease, well, that's given in the problem too. Look at that, it's perfect. So we got 0.07, and that's all over the probability of being an alcoholic, which is 0.05. All right, now if you were to work that out, that would be 0.14. Okay, so that's actually how you do that. So moral of the story, always use this as a denominator. Ask yourself, do I need to even go there with all this? Not necessarily, okay? Uh, you may be able to get away with that. Next moral of the story, write down variables representing the event itself. The event itself. Write down the probability of those events and any other probabilities they mentioned. Then you must plug it in to your structure, into your structure, and then solve it. So that's how that works. Okay, looking at this one. This one's a little bit more tricky. A magician has two coins. One is unbalanced and lands heads 60% of the time. The other is fair and lands heads 50% of the time. A member of the audience randomly selects, so that's an event. The fact that the audience randomly selects, that's actually an event right there. One of the coins and flips it. The result is heads. What's the probability that the fair coin was selected? Okay, so ultimately, what's the probability that the fair coin was selected given that the result was heads, right? That's how that's going to work. So we must get clear on the cast of characters. We will say that you represent the person selecting the unbalanced coin. Okay, selecting unbalanced coin. Okay, we'll say F represents the act of selecting the fair coin. And we could say H represents coin lands heads. Okay, these are all events. Now, we should be clear on the probability of all of these events, right? So the probability of the audience member randomly picking the unbalanced coin, well, that's 50%. We're going to assume that the magician just kind of held out two coins and the audience member looked at them and just randomly picked one, right? The probability of picking the fair coin would be the same. Okay. Now, this is a little bit trickier. We can't just be like the probability of heads. No, the probability of heads depends on which coin the person picked, right? So the probability of heads, given that it's the unfair coin, well, that's going to be 60%, right? That's given in the problem. It's literally right here. The probability of heads, given that a person picks a fair coin, well, that would be So now we must go on our mission to kind of make sense out of this structure and relate our cast of characters to this, which can be kind of hard, you know. Now, in this case, well, let's write down uh, this part, right, based on the question. So the result is heads. What's the probability that the fair coin was selected? So in other words, what's the probability that the fair coin was selected given that heads showed up, right? Given that heads showed up. So as I said before, always use this numerator for these problems. So we're looking at the probability of F times the probability of heads given F. Okay. Now, you should be breathing easy here because we have the probability of F. It's right here. We have the probability of heads given F. It's right here, right? So that's nice. We already know the numerator is going to be a piece of cake. But then we have to sort of make sense out of this. Now, I'm going to dive in here for the sake of avoiding confusion and start writing stuff. The reality is when they say A, we mean F. When they say B, we mean H, right? So this is really P of F, right? And this is really P of H given F, right? So that's important to know. Now this is P of not F, okay? So when it says not A, well, our A is F. So when they say not A, it really means not F, right? Now, what is F? F is the act of selecting a fair coin. So if we're talking about not F, we're talking about U. We're talking about selecting the unfair coin. So instead of using that little dumb prime symbol, I'm going to write U right here because that's what it means. Probability of not picking the fair coin times the probability of H given not picking the fair coin, picking the unfair coin, okay? So that could be tricky. I really understand it. So for my student at home, pause the video if need be, but their A is our F, their B is our H, so just kind of proceed accordingly. And when they say not A, what they really mean is the other event, okay? Well, what is the other event? It's this one, okay? So whenever you see the prime, it really just means the other event. Okay, so for my student at home, just know prime means the other event. All right, anyway, I don't know how many times I should say that. It's going to be kind of annoying. So I think you get it. We're looking at P of F times P of H given F plus, extend, plus P of the unfair coin times P of H given the unfair. Okay, great. Okay. Now, by the way, you might be wondering, well, why do we opt for this complicated one? Because this just says the probability of heads, you know? Well, what the heck is the probability of heads? It just completely depends on whether you pick the um, fair coin or the unfair coin. So anytime this thing depends on something else happening beforehand, yes, you have to go with this. Okay. In the previous problem, we didn't need, this one didn't depend on anything. In fact, this probability in the previous problem was literally given. In the problem, however, in this problem, the probability of this denominator depends entirely on whether or not you pick the unfair coin or the fair coin. Okay, so that's why you have to use this complicated mess. So P of F is 0.5. P of H given F, we already have that. That is 0.5. It's right here, right? Then we have P of F again. Okay, this is actually just a repeat of those two, right? And then we have plus the probability of unbalanced coin. Well, that would be 0.5. We have that right here. Okay, probability of picking the unbalanced coin. It's right there. It's right there waiting for us. Then probability of heads given that you picked the unfair coin. That's right here, zero point 0.6. Boom. What up? 0.6. Already there, right? So once you don't get freaked out by the prime symbols and just realize that means the probability of the other event as opposed to this event, it's not that bad. Okay. So when you work all that out in your calculator, it becomes approximately 0.45. Okay, and that makes sense. It should be it kind of makes sense that it would be less than 50%. All right, because there's more of a likelihood that the unfair coin would have turned up heads. It's a little bit of a mind bender, though, right? So thank God for Bayes' theorem. Thank God for this ridiculous denominator to help us when we don't know this probability, because this probability depends on some other stuff. Okay. Now there's a way of explaining all this with like a tree diagram, but my student already told me that the professor's not using tree diagrams, so I don't really want to load his brain with too many new things. I'd rather keep it very close to this structure. Okay. And don't worry about general form. That basically means that you see how you're adding this plus that. You might have to add more stuff depending on how many events there are. Okay. So that's kind of all this is saying. This is the sum of all the events, um, depending on how many events there are. Okay, so anyway, that's the Bayes theorem questions. Take care.